Alright, this is my third take on this exercise because I keep getting freaked out, as you might have gotten freaked out the first time you saw this problem, at the 1-point compactification thing, which probably for you hasn't come up for a while in this course, or at all if maybe you skipped over chapter 4 when you went through this, or just skimmed through it. I don't know. But because 1-point compactification doesn't appear a lot in this textbook, it might be a little scary, but it's fine because you're just adding 1 point, and so it doesn't make things any worse. Although it is good to just remind yourself what that means. So what you do when you take the 1-point compactification of something is you just take the original topology that you have on it, and then you add in more open sets. Well, you add a point, and then you add in another collection of open sets. These open sets are sets which contain this point infinity and whose complements are compact in your original space with respect to your original topology. So in this case, we've got y, and y has the discrete topology. So the 1-point compactification topology on X looks like you take the discrete topology and you add in open sets of the form infinity. Well, it's actually just complements of finite unions of elements in Y, because each point is not only open, but also every single point is closed. Right? Yeah, of course. Yeah, every single point is closed, and so compact sets end up being just finite collections of set. Like a set is compact when it is a finite collection of points, and so then complement. So basically, cofinite sets. Cofinite sets are also open. So X is the topology where all points, all singletons in Y are open, and all cofinite sets are open. But the cofinite sets we won't have to worry about, because those only deal with infinity, and infinity is just 1 point. And 1 point doesn't really matter when you're dealing with countability. So, now that I've rambled sufficiently, though not necessarily necessary, let's actually do some stuff. So let n be this, the complement of this support, which this is from exercise 2. This is a union of all u such that u is open and the measure of u equals 0. Okay. Since y has the discrete topology given any y and y, I'll try to make my little y squiggly and my my capital ones liney, such that the measure of the singleton set equals 0, then y is in n. So y intersected with the support of mu must therefore be precisely the set of points y and y, such that the measure of the singleton y is strictly greater than 0, because otherwise it's an n. Since X is compact and mu is Redon, measure of X is less than infinity, because Redon sets are finite and compact sets. So let's see here. Now assume, for a contradiction, that support u is uncountable. Then so is y intersect the support mu, because because the difference between x and y is just the point infinity. So you're only throwing out one point, so it doesn't matter. So let's see here. Then mu of x is going to be greater than or equal to the measure of the support of mu intersected with y, and that's equal to the sum over all y in the support of mu intersected with y of the measure of the singleton y. And so this is so if y intersected with support of mu is uncountable, then this is a sum over an uncountable set of strictly positive numbers. And what do we know about an uncountable sum of strictly positive numbers? This is going to be infinite. And that's a proof. It's kind of standard. It's a little more in the area of logic, but it's kind of one of those things that you should know at this point. Although it sort of falls into the category of things which no one teaches it to you in a class, but at some point you're just expected to have learned it in a class at some point before. So it's just in this kind of limbo of mathematical knowledge, because it doesn't really fit into a course anywhere naturally. You can actually find this at in the beginning in chapter 0 of Folland. So I would advise going back and reading that if you haven't seen it. But anyways, this is infinity. So this is a contradiction, because infinity is not less than infinity. Did I spell that? Contraction. That is not what I meant to. Contradiction. Probably been doing too much PDE. Hence, support of mu is countable. And this completes the proof.